Welcome to the deep dive. We are really thrilled to have you here with us today.
Yeah, glad you could join us for this one.
I want you to start by indulging a bit of a thought experiment with me. Imagine, just for a second, that you could completely dismantle one of the most famous foundational scientific theories of the 20th century.
Right, and we aren't talking about using, pages of complex algebra or building some multi-billion-dollar particle accelerator underground.
Exactly. I mean, completely dismantling it just by looking at a simple 3D shape from a slightly different geometric angle.
Which, sounds like a massive stretch.
It really does. But that is the precise journey we're taking you on today.
It's a profound shift in perspective. And frankly, it's a bit unsettling once you actually grasp it. Today, we're focusing our attention on a radical re-examination of Albert Einstein's theory of special relativity.
And our sources for this exploration are, well, they're highly unconventional.
Very. We are looking at a really fascinating series of blog posts and translated dialogue logs from an independent researcher, an author who goes by Zioned 2023.
Right, and what makes this material so compelling is that it documents this deep, evolving, and sometimes pretty argumentative conversation between this author and an advanced AI.
Yeah, together they're testing out a completely new geometric model of space-time.
And what a model it is. So our mission for you today is to unpack this mind-bending argument about how space and time actually work. We are going to focus purely on the physics, the geometry, and the massive philosophical implications of what the author and the AI uncovered.
But before we get into the weeds, we definitely need to establish a critical constraint for this discussion.
Yes, absolutely. So the author used Blender 3D, the popular 3D modeling software, to build these spatial simulations to prove their theory. And the source documents are just full of the underlying Python programming scripts used to generate those models.
Which can look incredibly intimidating if you aren't a coder.
Exactly. So critically, we are going to completely ignore those Python scripts. They are strictly reference material. It's just under-the-hood mechanics. Our focus is entirely on the concepts and the geometric realities that those visual simulations revealed, not the code itself.
That's a really important boundary to set. We don't need to read a programmer's loops and variables to understand the profound truth the code is painting. It's the visual, topological reality that matters here.
Okay, let's unpack this. To understand why this author's 3D model is so revolutionary, we first need to establish what it's actually rebelling against.
Right, to set the stage, we have to look at the standard textbook view of Einstein's special relativity, specifically the concept of Lorentz contraction.
The idea that space squishes.
Exactly. The universe has a strict speed limit, which is the speed of light, denoted as c. And for that speed to remain constant for absolutely every observer, regardless of how fast they're moving, Einstein and his contemporaries concluded that physical space and time had to be the variables.
So they have to change to make the math work.
Right. According to Lorentz contraction, if an object is moving at a significant fraction of the speed of light, its physical length must literally squish or shrink in the direction it is traveling.
So if a spacecraft flies past an observer at near light speed, the assumption is that the physical space the craft occupies is contracting. It physically becomes shorter.
That's the standard assumption, yes.
And this brings us to a highly revealing interaction in our source material. The user built a 3D model of a Michelson interferometer.
Which is essentially a cross-shaped device with mirrors used to measure light.
Right, and they had this 3D model moving through space at 60% the speed of light, 0.6 c.
A speed where those relativistic effects are supposed to be completely unavoidable.
Now, the AI analyzing the simulation data looks at the timeline. A flash of light is sent from the center down the two arms of the device, one pointing forward in the direction of travel, and one pointing perpendicular sideways.
The light bounces off the mirrors and returns to the center.
Exactly. And in the simulation, the light returns from both arms at a time value of precisely 250. The AI, which is trained on standard physics models, immediately assumes it knows what happened.
Of course it does. It calculates that for the forward-traveling light to bounce back at TAT equals 250 while moving that fast, the forward-facing arm must have been programmed to shrink.
Right, from a length of 100 down to 80. It just assumes the author manually coded Lorentz contraction into the simulation.
Because the AI is just doing the standard relativistic math. If the arm stays at 100, the light going forward has to chase the moving mirror. At 0.6 c, that forward trip takes 250 units of time just to hit the mirror and another 62.5 units to return.
Totaling 312.5.
Right. So the AI confidently concludes the arm must be 80 units long. That makes the forward trip take 200, the return trip take 50, perfectly matching the 250 total time of the transverse arm. It's airtight logic based on a century of accepted physics.
But wait, how did the AI react when the author corrected that assumption? Because the massive turning point of this dialogue is the author revealing there is absolutely zero shrinking programmed into the model.
Not at all.
The arms remain perfectly identically 100 units long. The physical apparatus did not squish, deform, or warp.
The AI was completely thrown off balance. It had to go back, parse the raw coordinate data of the 3D model, and confront the fact that the author was right. The physical object wasn't shrinking, yet the light was still returning at the exact same time.
Perfectly obeying the rules of a constant speed of light without needing physical space to warp.
Exactly.
I am still trying to wrap my head around that. If the physical wall of the mirror at the end of the arm isn't shrinking from 100 down to 80, how is the light reflecting off it to make the math work out so perfectly at exactly 250?
What's fascinating here is the geometric mechanism the simulation uncovered. The light isn't actually reflecting off a physically shrunken wall. It is reflecting off an invisible, mathematically perfect boundary in space-time called a spheroid.
A spheroid.
Right, because the device is moving at 0.6 c, the locus of points where light can reach and return simultaneously forms an elliptical sphere, a spheroid around the origin point. The physical arm is still length 100, extending beyond this invisible boundary. But the light pulse's interaction is governed by the spheroid geometry in the electromagnetic field, not the physical edge of the metal arm.
That feels like a massive conceptual leap.
It is.
The author uses a specific geometric metaphor to explain how this works visually, relying on 3D shapes instead of complex algebra. Imagine a 2D plane representing space. Draw a perfect circle on it. The circle represents the physical interferometer apparatus.
Okay.
Now, add a vertical axis for time and imagine that flat circle moving smoothly upward through time. If you trace its path, that flat circle sweeps out a long 3D cylinder through space-time.
That cylinder represents the true, unwarped reality of the object existing over time. In a four-dimensional Minkowski spacetime model, reduced to 3D for our visual comprehension, this cylinder is the objective truth of the object.
Okay, I follow that.
But the illusion of shrinking that Lorentz contraction we discussed earlier comes from how different observers interact with that cylinder. It all depends on how an observer's frame of reference slices through that 3D cylinder.
Let's break down those slices. It reminds me of looking at architectural cross-sections, where the angle of your cut completely changes the shape you see on the paper.
That is an excellent way to conceptualize it. Let's examine the stationary observer. Someone standing on a platform watching this object fly by at 0.6 c.
Oh, right.
For this stationary person, their experience of a simultaneous moment is a perfectly flat, horizontal slice across that moving space-time cylinder. But because the cylinder itself is moving diagonally through space-time relative to them, slicing it straight across horizontally yields a cross-section that isn't a perfect circle.
It's an ellipse.
Exactly. It appears squished in the direction of travel.
So the stationary observer looks at that elliptical cross-section and assumes the building itself is warped. They say the object physically contracted. The arm shrank from 100 down to 80.
They are mistaking their specific cross-sectional slice for the objective three-dimensional reality of the object.
Right.
But now, examine the observer who is moving with the apparatus. For them, their simultaneous moment is not a flat horizontal slice. Because they are moving, their moment in time is a tilted slice through that space-time cylinder.
Diagonal cut.
The geometry dictates that if you slice that moving cylinder at the specific diagonal tilt that corresponds to the observer's velocity, the resulting cross-section is a perfect circle. It maintains the exact same pristine radius of 100 that it always had.
This is a huge paradigm shift for you as a listener to digest. The physical object isn't crushing inwards. The universe isn't physically warping solid matter just to satisfy an electromagnetic speed limit. It's simply that different observers, moving at different velocities, are taking differently angled topological slices of the exact same unwarped reality.
Precisely. The stationary observer takes a horizontal slice and sees an ellipse. The moving observer takes a tilted slice and sees a circle.
Neither observer is hallucinating, but the stationary observer is fundamentally wrong to assume the object physically deformed.
It completely reframes special relativity from a physical deformation of matter into a geometric reality of differing perceptual slices. And this naturally leads us into one of the most famous paradoxes in physics history. The author uses this new geometric framework to completely deconstruct Einstein's train paradox.
The train thought experiment is cited in almost every basic physics class, but honestly, the simultaneous events aspect has always tripped me up. How does this new topological slice view change what happens on that train?
Let's review Einstein's original setup. You have a train moving rapidly down a track. A passenger is standing dead center in a train car. A flash of light goes off right where they are standing.
Yeah.
Einstein stated that to the passenger inside the train, the light travels outward and hits the front wall and the back wall at the exact same time. It's simultaneous.
Right.
However, to a person standing still on the station platform, the back wall is rushing forward to meet the light beam, hitting it earlier, while the front wall is running away from the light, taking longer to hit. Therefore, events that are simultaneous to the passenger are not simultaneous to the person on the platform.
And Einstein used that to prove simultaneity is relative, but where is the hidden assumption the author found in that logic?
The hidden assumption is in how Einstein defined the observer inside the train. Einstein argued that any moving observer can arbitrarily pretend they are completely stationary. He said the passenger can just define their velocity as zero because all inertial frames of reference are mathematically equivalent.
And the author disagrees with that.
Strongly. The author introduces a radical philosophical departure here, redefining what it actually means to be an observer in a physical universe.
Are they saying you can't just zero out your velocity just because the math lets you?
Precisely. The author argues that we must define an observer's local point by 3 distinct parameters, not just 2. Historically, you define an observer by their spatial location, let's say x equals 0, and their temporal location, t equals 0. But the author insists you absolutely must include your velocity, v, relative to the electromagnetic field.
You cannot simply ignore the fact that you are moving through the medium where light travels.
If we connect this to the bigger picture, the observer is trapped at this local point. If you accept that the passenger on the train actually has a velocity greater than 0 through the electromagnetic field, you don't need physical space to shrink.
Because you aren't stationary.
Right. Instead, the observer is simply moving towards delayed information coming from the front and moving away from delayed information coming from the back. You are a biological receiver catching light rays that have traveled different distances and taken different amounts of time to reach your specific moving coordinates.
I see where this is going. Your brain acts as a processor. The light from the front of the train and the back of the train arrive at your retinas. Your brain then takes these scattered, differently delayed signals and reconstructs them into what you perceive as a real, instantaneous physical space around you.
Yes. Space itself isn't physically contracting. The information about that space is just arriving diagonally through time because of your movement. The geometry of the Blender simulation proved that you don't need a physically squished train car. You just need to account for the tilted slice of information arrival.
And this highlights what the author boldly claims is a massive cognitive trick that Einstein fell for. The source material gets quite critical of historical physics here. The author argues Einstein literally tricked himself with his own mathematical map.
He started with a strict mathematical definition. Einstein rigidly defined that light must take the exact same amount of time to go forward in a moving train as it does to go backward, from the perspective of the passenger. He baked that assumption into the core of his equations.
And then he just ran with it.
He mistook that arbitrary mathematical constraint for physical reality. He forced the physical universe to warp and shrink to fit his math, rather than letting the math objectively describe a rigid universe.
So what does this all mean? Why does a debate about an old physics paradox and a 3D computer model matter to you listening right now?
It matters deeply because the author is pointing out a systemic flaw in how we model reality. The entire field of theoretical physics arguably got so deeply lost in making the math work on paper that they forgot to verify if it matched the physical territory. In philosophy, there is a famous axiom: the map is not the territory.
The map is not the territory.
The equations, the mathematical formulas, those are just the map. The actual tangible universe is the territory. Physicists drew a map where lines curved, time dilated, and objects shrank. Instead of taking a step back and saying, maybe our map is drawn from a skewed perspective, they declared the actual ground must be curving and shrinking. They accepted physical absurdities to keep the math looking elegant.
It's a profound lesson in critical thinking that applies far beyond theoretical physics. I am reminded of a time I was driving in an unfamiliar city, relying entirely on my GPS. The map on my screen showed a road going straight ahead. The physical reality outside my windshield showed a boat launch leading directly into a lake.
Oh no.
Yeah. If I had blindly trusted the map over the territory, I would have driven my car straight into the water. And we do this all the time with data. You might have a flawless financial projection on a spreadsheet or a beautifully balanced corporate strategy on a whiteboard, but if executing that model demands that human behavior or physical reality must unnaturally deform to make it work, your model is flawed. The map is not the territory.
And that is the true value of the author's blender simulation. It proves that if you change your foundational assumption, if you stop assuming solid objects physically shrink and start assuming that moving observers simply take differently angled topological slices of a rigid 3D reality, all the math of relativity still functions.
The light still arrives exactly when it is supposed to.
The speed of light remains constant. But suddenly, the universe makes logical sense again. Objects remain solid. The territory remains intact.
We've spent this deep dive unpacking how a geometric approach completely upends a century of assumed physics. And it wasn't achieved by discovering a new subatomic particle. It was achieved by proving that sometimes the universe doesn't squish. Our perspective just tilts. We traveled from the rigid, unshrunken arms of an interferometer to the angled slices of space-time cylinders, all the way to redefining the observer as a local point, a receiver trapped in a web of delayed information.
This raises an important question, one that pushes beyond historical paradoxes and looks toward the future of technology and our understanding of the cosmos.
What kind of future implications are we talking about here?
If the author's theory holds, if spacetime is not a physical container that warps, but rather a rigid geometry, where distance and time are just tilted projection slices based on our local point, how does this reframe our current hurdles in physics? Think about quantum entanglement, where two particles seem to communicate instantly across vast distances, which we currently call spooky action at a distance. Or think about the theoretical pursuit of faster-than-light communication networks.
Are you suggesting that if distance is just a perspective slice, those distances might not be as absolute as we think?
Exactly. If we are currently building quantum computing models or FTL theories based on the assumption that space physically stretches and shrinks, we might be using the wrong map. If entanglement is just two particles sharing the exact same coordinate on a different dimensional slice, rather than physically crossing a vast warped void, it changes the fundamental engineering of how we might harness that technology. We might be fighting against physical deformations that don't actually exist.
That is an incredibly provocative thought to leave you with. If our foundational map of the universe is built on a cognitive illusion of shrinking space, what technological breakthroughs are we currently blind to simply because our perspective is tilted the wrong way? If two people can't even agree on the shape of a simple circle because of how they happen to be moving, how can we ever claim to see the world completely objectively? We want to thank you so much for joining us on this deep dive today. We hope this challenged your assumptions and gave you a new lens to view the world. Keep examining the cross-sections of the information you receive, keep questioning the maps you are handed, and never forget to look closely at the territory around you.